So far in Calculus 1, what we've done is we've talked about limits in a very intuitive sort of way. So that means we've looked at limits from either the graph standpoint or from the numerical standpoint, where we just kind of plugged in numbers or looked at the graph and kind of saw where it went, and we made our best guess as to what was happening. And in that case, it's a very kind of plain English sort of definition as to what a limit was. We just looked at where it was headed. And so what we need to do now, since we are in Calculus 1, we need to start kind of looking at it from I'm going to use the word more precise or more rigorous kind of definition that's mathematically correct. And so what I'm going to do right now is talk about, again, the precise definition of a limit. And you probably have realized that over my shoulder here, there's some symbols that you haven't quite seen before. And so I'm going to go ahead and mention what those two symbols are real fast. First off is this one that kind of looks like an E or maybe a backwards 3. What that symbol actually is, and yes, it really and truly is Greek. It is the letter epsilon. That's what we call it. It is the Greek letter E. In this case, it's the lowercase letter. The other one is, it almost looks like an S that curls around and touches back on that curve. And so what that one is actually, it's delta. Which you're probably realizing it kind of looks like a squiggly lowercase d at this point. And that's a good way to explain it too. It is a squiggly lowercase d. And in fact, that is the lowercase letter d in Greek. It's delta. We will talk about an uppercase letter D, the uppercase delta later. That one's actually shaped exactly like a triangle. But for right now, we just need these two lowercase letters, epsilon and delta. And so what I'm going to go ahead and do is make sure I mention that this precise definition also has another name. It's also known as the epsilon delta definition. And you're going to see why we kind of have them in a weird order in just a second. Again, epsilon is E, delta is D. You'll see. So we're looking at the limit as x approaches n of f of x equals some number L. That's our limit. And so what we're doing is we're going to describe it mathematically. So for every epsilon, so for every number that's greater than 0, then there should exist some delta, some other number that's also greater than 0, such that if this distance, 0 is less than the absolute value of x minus n is less than delta, then the absolute value of f of x minus L is less than epsilon. Now, again, that's a very rigorous definition. That's a very mathematically complex explanation of it. So one of the things I want to kind of throw back to you is, in case you did not already know, absolute values just describe distance. So here's what's happening here. We're talking about the distance around x, okay? So like I said, in this case, we're talking about some x distance, and we want it to be close. We want it to be within delta, okay? What we're also going to look at here in this case is another distance. In this case, a distance from f of x. So a y distance. Now, we want that to be less than epsilon. So what we're talking about, and I'll kind of quickly sketch a picture, is we're talking about having this graph, and I'm going to draw one real fast, just for fun. Okay? So there's my graph. And what I want is I want to find a limit as x approaches n. And we want it to be some number L. And all I want to do is make sure that, again, I'm trying to be very specific here, that we're close enough. Notice my words, close enough. So what I'm looking at here is essentially how close on either side do I need to be from n, and that's going to be delta on both sides. Do I need to be so that my limit is going to be within epsilon of L? So essentially what I'm trying to do is I'm trying to find some number, some x values that are going to make it so my y values are really, really close. It kind of goes back to that intuitive definition again. So let me repeat one more time. We plugged in x values as they got increasingly closer to the limit I was looking for, and we hope that the y values also got increasingly closer and closer and closer to the answer. And so that's what I'm doing here. I'm just now using new symbols, new letters. In this case, epsilon and delta. Delta just tells me how far from the x values should I go, and epsilon tells me how far of the y values are acceptable to me. Now, The reason I said I was coming back to why we do epsilon and then delta, here's the thing. What we're going to do is we're going to use epsilon first for every epsilon. We're going to use epsilon first to kind of put a restriction on what my deltas can be. Now, you're going to see that in a couple of examples in just a few minutes, and I just wanted to make sure, again, this is also known as the epsilon delta definition. We have to know epsilon first.